Hey, what's up everyone? In this video, I'm going to be talking about binary numbers. We're going to be covering a bunch of different topics in a short amount of time, but I promise you it'll all make sense at the end. So we're going to cover things like what binary numbers are, then we're going to cover different unit variations like bit, nibble, and byte, then we're going to go over something called short notation. Then we're going to convert from binary to decimal, and then we're going to convert from binary to hexadecimal. We're also going to go over some binary math like addition, subtraction, multiplication, and division. And then lastly, we're going to go over logical operations. All right, so let's get started. All right, so what are binary numbers? So behind every electronic device, there are a ton of switches. And these switches control the flow of current within the device. And with this, the device is able to do what it does. And so to represent the flow of current, we use something called binary numbers. And so a binary number can look like this. Think of it just like a switch. It could either be on or off. Or you could also see it as 0 or 1. Okay? It's going to have one of two states. Okay? Either 0 or 1, or off or on. Now let's go over unit variations. So let's say you have just one switch, okay? And this switch can be either on or off, okay? But the important thing is that if it's just one digit, this is known as a bit. Now if you were to have, say, 4 switches like this, okay? And again, these could be on or off, 1 or 0. 1, 2, 3, 4. If there are 4, then this is known as a nibble. And if there are 8 switches, 1, 2, 3, 4, 5, 6, 7, 8, this is known as a byte. All right, so now we're going to learn about something called short notation. Now this is pretty straightforward. Let's say we have a byte. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And if I were to bring down this other binary number here, and what if I were to tell you that these two numbers had the same value? The reason for that is because with binary numbers, you can actually get rid of the zeros that are together on the left side. So if I were to get rid of these zeros, these two binary numbers are exactly the same. Now, another thing is that when you're dealing with binary numbers, you will normally see this percent sign in front of it. And the reason for that is because this lets us know that this number is a binary number and not a regular number. So for example, this is not 11,010, but instead it is the binary number 11010. All right, folks, so now we're going to convert from binary to decimal. The way we do that is we write down our binary number. So here we have 1, 2, 3, 4, 5, 6, 7, 8 bits. And remember, 8 bits is equal to 1 byte. So this whole thing here is 1 byte. Now the next thing is we write the powers of 2 right above it. So here we have 2 to the power of 0, and anything to the power of 0 is 1. 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 2 to the power of 5 is 32, 2 to the power of 6 is 64, and 2 to the power of 7 is 128. Now what we do next is we line them up all together like that, okay? And remember how I said that bits are sort of like switches? So if it's a 0, that means it's turned off. And what we do is, if it's turned off, then we get rid of that power, okay? So this one is also turned off, so we get rid of this one. This one is turned on, so we leave this power. This one is turned on, so we leave this power. This one is turned off, so we get rid of this one. This one is also turned off, so we get rid of that one. This one is turned off, so we also get rid of this one. And then this one is turned on, so we leave this power right there, okay? And then all we have to do now is just add all the powers that are left. So 4 plus 8 is 12, and then 12 plus 128 will give us 140. So this binary number is 140 in decimal, okay? So this and this are the same, all right? Now converting this binary number to hexadecimal is just as easy, okay? Maybe even easier. All right, so what we have to do is we have to bring back our powers of 2 and line them up back again, like that, okay? Now the trick here is that we actually have to split the binary number into nibbles. Remember, nibbles are 4 bits. So 1, 2, 3, 4. So these are 4 bits. So this is one nibble. 1, 2, 3, 4 bits. So this is another nibble, okay? So here the powers of 2 are lined up pretty well, but here we actually have to start our powers of 2 from the beginning, just like here. So this will have to be 2 to the power of 0, which is 1, and then 2 to the power of 1, which is 2, and then 2 to the power of 2, which is 4, and then 2 to the power of 3, which is 8, okay? So it's identical to this one here because we're treating these as separate nibbles, all right? So this is one nibble, this is another nibble. And then all we have to do is we line them up all together and we check to see which one is turned on and which one is turned off. So this one is off, so we get rid of this one. This one is turned off, get rid of this one. This one is turned on, so we leave this one here. This one is also turned on, so we leave that one as well. This one is turned off, so we get rid of this one. This one is turned off, so we get rid of this one. And then this one here is also turned off, so we get rid of this one. This one is turned on, so we leave this one here, okay? Now all we have to do is we add the numbers, okay? We add the powers right above, but we don't add them all across. Remember, we're treating this one as one nibble, and we're treating this one as a separate nibble. So we're just adding these two. So 4 plus 8 will give us 12, okay? Now here's the thing about hexadecimal numbers. The range for hexadecimal numbers is 0 through F, okay? So if the number that you're looking for, okay, is greater than 9, then you're going to have to use one of these letters, okay? So for example, if you're going to use 10, then you use the letter A. If it's 11, then it's B. 12 is C, 13 is D, 14 is E, and 15 is F. So because 4 plus 8 equals 12, we don't just write down 12, we actually use the letter C, okay? So this C lines up with this nibble here, okay? And then we do the same thing here. So the only powers of 2 here is this one, is this 8, okay? So we don't need to add anything else to it, so we just write down the 8, okay? And that is how we write that binary number in hex. So this binary number and this decimal number and this hexadecimal number, they're all the same thing, okay? All right, so now we're going to cover adding binary numbers. So here we have 2 bytes, 1, 2, 3, 4, 5, 6, 7, 8. So we have 1 byte here and 1 byte here, and we're going to be adding them together. So we start off by adding the numbers all the way to the right. so 0 and 0 is of course 0. So this one's easy. Here, we add 0 and 1. That, of course, will give you 1. This one here is a little bit more tricky because we're going to be adding 1 and 1, but because we're dealing with binary numbers, our answer is not going to be 2, but instead it's going to be 0. We're going to have that carryover 1, and it's going to go up here. Now this right here is probably the trickiest part of adding binary numbers. What you do is you add this carryover 1 to this one, and of course that'll give you 0, right? So here we have 0. Then we get a carryover 1 from those two numbers that we just added, and we put that carryover 1 here, okay? Now this gets added to this, and of course we get 1, right? Because 0 plus 1 is 1. Now here, 1 plus 0 plus 0 is 1, okay? Here, 0 plus 1 is 1. 0 plus 1, again, is 1. And then here, 1 plus 1 is going to give us 0 with that carryover 1. And then because we don't add it to anything here, we just bring it down. And this is our answer. 1, 0, 1, 1, 1, 1, 0, 1, 0. Now, because of this extra bit here, okay, notice how we have, there's 8 bits here, and then there's 1 extra bit here. So we have a total of 9 bits, okay? So sometimes you might see the result as this, and sometimes you might see 3 additional zeros in front of this one. So here to the left, okay? Now the reason for that is because they want to, depending on the calculator or the application, it's going to add on 3 zeros, 3 leading zeros to the left, just so the whole number can be either a byte or they want to do everything by nibbles. It really depends on the calculator or the application, but the result is going to be the same. If you have this number, okay, just the way it is, or the same number with 3 zeros in front, they both mean the same thing. All right, so now let's cover subtracting binary numbers. So here we have 1 byte, here we have another byte. So we start on the rightmost side by doing 0 minus 0, which will give us 0. Then we do 1 minus 0, which will give us 1. Then we do 0 minus 1, which will require this 0 to borrow from the one to the left of it. Now this 1 turns into a 0 because we're borrowing from it. And the trick here is that 2 ones get borrowed over, like that. Now we can do 1 minus 1, which is 0, and this one is sort of left hanging, so we can bring this one down, like that. Now here it's the same thing. 0 minus 1 will require this 0 to borrow from the one to the left of it. So this one turns into a 0, and remember, the trick here is that 2 ones get borrowed just like that. So now we can do 1 minus 1, which is 0, and then this one is sort of left hanging. We can bring this one down like that. Then we do 0 minus 0, which is 0, and 1 minus 0, which is 1, 0 minus 0, which is 0, and 1 minus 1, which is 0. And this is your answer. All right, so now we're going to go over how to multiply binary numbers. So here we have a byte, which is equal to 12 in decimal. And we know this because if we look at the powers of 2, 4 plus 8, that's 12. You'll notice that all the other powers of 2 are turned off. So that's how we know that this binary number is equal to 12 in decimal. And basically what we're going to be doing is we're going to be multiplying that 12 times 2. Now this trick is very easy but it only works with multiples of 2. So you can't do like 12 times 3 or 12 times 9 or something like that, right? It could only be multiples of 2. Now we know that 12 times 2 is 24, so that's pretty easy, right? But how do you do that using binary numbers? Well, the only thing you really have to do is you have to shift to the left when you're multiplying. So if we're multiplying times 2, okay, we only have to shift once, like that. And because we have an empty space here, you can just fill that in with a 0, just like that. And this right here is now 24, and I'll prove it. You'll see these powers of 2 are all turned off. This one is 8, this one is 16. The rest of these are turned off. 8 plus 16 is 24, and that's how you get your answer. And if you want to multiply this 24 times 2 again, all you have to do is you shift it over to the left. And then because you have this empty space here on the right side, you can always fill that space in with a 0. Okay? So now you have all these empty spaces. You have 16 plus 32, that's 48, which is 24 times 2. And so on. And you could sort of keep doing the same thing over and over. But remember, this only works with multiples of 2. All right, so now we're going to go over how to divide binary numbers by multiples of 2. Now this is a very easy trick, very similar to the multiplication trick. And again, you can only do this with multiples of 2. And this is how it works. So here we have the number 48 in binary. Okay, so that's 48. How do we know that? Because if we look at the powers of 2 right above these bits, you'll see that the only ones that are turned on are the 16 and the 32. So 16 plus 32 is 48. Now, when we want to divide by 2, all you have to do is you shift these bits over to the right, like that. So every time you want to divide by 2, you move it over to the right by 1 bit. Okay, you'll notice that this space is empty here, so we could just place a 0 there. Okay. And now look at the exponents and see which ones are turned on and which ones are turned off. And then you will have your answer. So here you'll see that 1 is off, 2 is off, 4 is off, 8 is on, 16 is on, and the rest are off. So 8 plus 16 is 24. And remember, we started off with 48, and you divide 48 by 2, and of course you get 24. And just remember, this trick only works with multiples of 2. All right, so now we're going to go over logical operations. And the first operator that we're going to go over is AND. You might also see it as this symbol here. So what AND is looking for is that when you have all your bits lined up, you want to make sure that both of them are 1, and that'll result in 1. So here, let's go over an example. You see how these are both 0? Well, that one will result in a 0. This one here is a 1, and this one is a 0. So this one will also result in a 0. Because remember, we're looking for both of them to be 1. Now here, both of them are 1, so this will result in a 1. This one here is the same thing, right? They're both 1s, so it'll result in a 1. Now here we have a 0 and a 1, so that'll give us 0. These two right here are 0, so that'll be 0. This one here is a 1, this one's a 0, so that'll give us a 0. And these two here are 1s, so that'll give us a 1. Now notice, the only ones that are 1s are the ones that have both bits as 1s. All right, so now we're going to go over the OR operator. And you might also see it as this symbol here. Okay. So the way this one works is it wants to check to see if either bit is a 1. And if it is, then that results in a 1. So let's go over an example. So here we have 0 and 0. Are any of those 1s? No. So that results in a 0. Here we have 1 and 0. Are either of these 1? Yes, this one's a 1. So we have at least 1. So that results in a 1. Here we have a 1 and another 1. Are either of these 1s? Yes, actually both of them are. But we only really just need 1. The result is 1. Now here it's the same thing. We have both 1s. So that results in a 1. This one we have a 0 and a 1. So that'll give us a 1. Here we have 2 0s. So that'll give us a 0. Here we have a 1 and a 0. Remember, we only need at least 1. Okay, so that results in a 1. And of course here we have 2 1s, which will give us a 1. All right, so now we're going to go over the exclusive OR operator. You might also see it as this symbol here. And the way it works is it's very similar to the OR operator, where either one has to be 1, okay? But if both of them are 1, then it actually results in a 0. So here, let's go over an example. So here, remember, it's very similar to OR. So if either one is a 1, then the result is 1, okay? So here we have 0 and 0, which is 0. Here we have 1 and 0. Now we have at least 1, right? So that results in 1. Here we have 2 1s, okay? Now you might think, oh, okay, well, we have at least 1, so it'll be 1. No. Whenever you see 2 1s in an exclusive OR operator, it actually results in a 0. Okay. Now here we have the same thing, 2 1s, so that'll result in a 0. And then we keep going here, 0 and 1. Now we have at least 1, so that results in a 1. Now here we have 2 zeros. When we have 2 zeros with an exclusive OR, it's still going to be 0. So that's a little different than this one. So 1 1 will equal a 0, but a 0 0 will still equal a 0. Okay? Now we have a 1 here and a 0 here, so we have at least 1 1, so that results in a 1. And then finally, we have the 2 1s here again. So remember, just like this one, if there's 2 1s, that results in a 0. All right, so one more thing to note about the exclusive OR operator is that you know how here we have all these bits and then we have all these bits here, right? And we were working from top to bottom, and this was our new answer. Well, keep in mind that if you were to use this row of bits and then do an exclusive OR using the ones right above it, the row of bits at the very top will be your new answer. So here, let's go over an example real quick. So remember, we're using the exclusive OR operator. So 0 and 0 will give you 0. 1 and 0, now remember, at least one of them has to be 1. So we do have at least 1, so that'll give us 1. Here we have 0 and 1, so we need at least 1, so the answer is 1. Here we have 0 and 1, so it's the same thing. That results in 1. Now here we have 2 1s. Now remember, we're using the exclusive OR operator, so because both of them are 1s, that results in a 0. Here we have 2 zeros, that results in a 0. Here we have a 1 and a 0, so at least one of them is 1, so that results in a 1. And then finally here we have a 0 and a 1, and because at least one of them is a 1, that results in a 1. So hopefully that helps.